So now we're going to take all that we've learned in the past couple lessons and apply it to something a little bit more practical. So we're going to create a new geometry object. We're going to dive into this and we're going to make a grid. Zoom out on that, and we're going to do kind of what we did before. Going to make it a nice dense grid, make it even more dense just for fun. We'll make it a little bit larger as well, just because why not? We are going to add some noise onto it. Before I did a mountain node, I think there's better ways to apply noise to something with more control, so I'll just do it quickly, just as a quick example. I don't like to do much in point VOPs, but one thing that I do pretty frequently is add noise. It's pretty easy to do it in point VOP and not quite as easy to do it in a point wrangle. So we're going to make a point VOP. And so what we need to do, and one thing that it took me a long time to learn when I was just first starting out in Houdini, is I didn't quite understand how these worked. But it's actually pretty simple. So first I want to take some noise, and one pretty common noise pattern to use is turbulent noise. There's also anti-aliased noise. There is unified noise. There's all sorts of noise that you can use. I usually fall back between turbulent noise and anti-aliased noise, but your results may vary. So right now I'm just going to use turbulent noise. So what we first need to do is tell the noise where in space the noise needs to be. And so we're going to say wherever the position of this grid is where we want the noise. So I'm going to put that there, feed it into the position. And so what I used to do when I didn't know what was going on is first we want to export 3D noise, which just puts noise in various directions all around instead of just from a 0 to 1 value. So this will give us values in X, Y, and Z. So I'll set it to 3D, and so then I'll be like, okay, I got my noise, and put that into position. And you can see that it broke. And that's because we want to take the noise and add it to what we already have. So instead of just plugging it into position at the end, we want to add the noise on top of the position of each point. So now if we do this, whoop. Now we have some noise. Another thing that you should probably do is, yeah, you can go into here and change all the settings, but it's best to do it outside of a point VOP. There's different noise types, and the noise type is, I guess, how it adds noise and what range of number that it adds noise to. So you'd have to look it up online, but basically like simplex noise is, I think it might be 0 to 1. I'm not exactly sure, but I guess I'll show you real quick. If you aren't sure, you can go to any node that you are unsure about and want to know a bit more about. So I'm going to go to here, and then this question mark brings up the help docs. Takes a hot second. And so then we can see that Perlin noise gives you numbers from -1 to 1. Sparse convolution, -1.7 to 1.7. So there's various ways in which noise is added. I generally use simplex and Perlin, but it really depends on what you're doing. So anyways, let's do some simplex noise. And so then if you go into any of these nodes, you can promote it to SOP level instead of, we're in the VOP context right now. 1 up is the SOP context. So I don't want to deal with anything in here. So I'm going to middle mouse click this, and then I'm going to promote parameter, and I'm going to do this for each one of these. Except for attenuation, I don't really care about that one. So now that this is up here, I can change the frequency. I'm going to lower it. I want larger mountainous stuff. So amplitude is how much noise we're actually applying. And so this looks pretty good. I'll make it less rough. So let's say I wanted this to undulate for some reason. I could give it an expression of time. And so time, the offset, so offset just to show quickly, so I can move the noise pattern along an axis. So this is moving it along X, moving this along Y, which just makes it a little bit more undulation looky. You can't really see what plane that it's moving on, whereas X and Z, you can clearly see how it's moving. So let's say I wanted this to just look like it's undulating. I could do at time. And so every frame, it's going to keep moving forward in time and do that. And I do this all the time. If I need to offset noise, this is what I'm doing. I do it constantly. It's something that's really helpful to know. And now that we have our noise pattern, I'm going to scatter some points. Another thing that I do literally all the time. So now I got my points. And so one thing that I need from these points is I'm going to copy things to these points. I don't want as many as there are now, so let's just cut it by, so we only have 300. And if I look to see if they have normals, they don't have any. And the reason they don't is because these points will inherit a normal from the surface that it's scattered onto, but the surface doesn't have a normal. So there's two ways to apply normals. One of which is the way that I do it, because I guess it's old school, and it's a facet node, and there's a lot of things that the facet node does, but pretty much the only thing I ever use it for is I can pre-compute normals. And then now if you look at the geometry spreadsheet, it has created normals, which basically just shows the direction in which every point is facing. And we can look at it like this. And that's helpful. Another way to do it is to drop a normal node or normal SOP. And the one thing, I guess the reason I don't really use this as opposed to the facet is it's this one I have to click a checkbox. This one I have to choose a drop down, because this defaults to creating normals on the vertices, which I basically never use. And now I have to change it to points. Otherwise, normals are normals. Doesn't really matter how you get them. I'm going to be using facet just because I prefer clicking a checkbox. So now if we look at the scatter, we can see that each of these points have normals. So let's say I wanted to add a bunch of pillars to the surface of this. Like they could be a substitute for trees. There's some ways to go about it, but they're all kind of based off of where these normals are facing. And there's a lot of ways to manipulate these normals to get various looks. So first, I'm going to do a copy to points. And I'm going to take a box. Before I start messing with this, I want to just build sort of a quick little pillar. And I want its base to be at origin. So just a quick way to do this is I'm going to use just a quick edit SOP. There's other ways that are more procedural to do this, but since this is just a quick example, I'm going to do it the less elegant way. I'm going to scale it in a bit. Alright, so now I've got a pillar. And if I want to put this onto where these points are, just going to feed that into there. And so the first thing you'll see is that it is doing what it should be doing, but it uses the z-axis instead of the y-axis to denote up. So what I would need to do is rotate this 90 degrees. And by 90 degrees, I mean I need to rotate this by 90 degrees. So we can see now that all these pillars are, in fact, following the normal that it's been copied to. So first, I think we have too many pillars. I'm gonna narrow this down a bit. Let's just do 150. Alright, and so let's say I wanted them all to face up. Well, I've shown you that before. We can just drop a point wrangle. And I can just say, no matter where the face is facing, I want the normal to just be going up. So I can do @n equals curly bracket 0, 1 for the y-axis, so that it's facing up, 0, semicolon, and now all those normals are facing up. All my pillars are facing up. And that's pretty cool. But let's say I want all of the pillars to be facing inward. Where would you begin to do that? And so that brings me to something new that we're going to learn, and it's called get bounding box. So I'm going to just delete this, and then I'm going to take this grid that I have, and I want to find the center of the grid. And so one way that you can do that is you can look at the bounding box of this. And so now I can drop a bound, which gives you a bounding box for whatever object you want, which is just a box that entirely encompasses an object. And so from here, there's a function that calculates where the center of this bounding box is. So what I'm going to do is I'm going to create a position. And that position, since it needs to know where it is in x, y, and z, is a vector. So I'm going to make a spare parameter or a local variable, call it vector, and I'm going to say cent for center equals get BB or bounding box or B box center, and then we just want the bounding box of this specific object. And now nothing's going to happen. And that's fine. Because what we need to do is take this position, so the center, and then we need to subtract that by the position of each other point on this grid. So now we will do normal equals at position, so the position of each point, minus the center point. And of course, I always do it wrong, so it actually has to be the other way around. And now everything is facing towards that. And so this might seem strange, but basically all you need to know about this, and I'll just do a quick example. I'm going to do add. We're going to look at this. I'm going to make a new point. I'm going to move it up in space. Then I'm going to make another add. I'm going to make another point. I'm going to move this a little bit up in space and a little bit over. So now we have 2 points. A point here and a point here. Neither of them have normals. Let's say that we want a normal where one of these positions is facing another position. You just have to take the position of one point and subtract it by the other point, and that will give you a vector or a position of one point and how it is facing the other point. So I'll do a point wrangle. And then I'll take this here. And so now let's say I want that vector. I can do normal equals, so the position of this point at P minus, and then I want the position of the other add that I made, and it's in the second input, or input 1, because it goes 0, 1, 2, 3. So what I need to do is I need to look at a point attribute. So I'm going to do point, which looks up point attributes in other inputs. So I'm going to say that I want the point attribute from input 1. And then it wants to know, well, what attribute are you looking up? And so that you have to make a string. Strings are in green. And I have to say it's P, or position. And then just tell me by the point number which position it is. And so of course I always do it backwards. And I forgot an at. So now this normal will always be facing this point. So let's just merge the two. Now if I transform this point, yes. Now when I transport this or transform this point, this normal is going to follow wherever I put this point. And so I won't really get into the how it creates this vector, but just know that it does, and it's very, very useful. Subtracting one position from another position will always give you the direction in which one point is to another point. So that's what we've done here. So everything's facing the center now, and that's great, but if I copy these onto here, they're all going to be facing the center. And let's say I just want them to kind of be facing center. Well, there's a few ways I can change how this works. One of which is I can edit this normal individually from each channel. So let's say I want things to be facing up a bit. I can do @n, and so if we look down here, there's nx, ny, and z, and it corresponds to each direction. So I want to change the up direction of this normal. So I'm going to do n.y. And then, let's see, I'll just take what the position already is and add to it. And so whenever you want to add something on top of itself, you do plus equals, just as if you wanted to multiply it, you do times equals. And so really all it's doing is saying n.y equals @n.y plus something, but you don't want to have to type that all the time, so you just do plus equals. And so again, I want to add in a channel without having to type a bunch of stuff, so I'm going to create a float channel and do y add. And now everything is going up. And I can do this. So that's pretty nifty. And then I can get it standing all the way up. I can go down. I can make it go down like that. And you can do it for each position. If I wanted things to sway in the x-axis, I can do @nx, x add, and there you go. So that's kind of fun. So I want to change the size of each of these pillars. I don't want them to all be exactly the same. So a good way to do that is to go back to our old pal P-scale and start changing that. So another point wrangle. And we're going to do @P-scale equals fit 01 rand pt num min max. Again, I said I've typed this a bunch of times, so I'm getting pretty good at it. So of course it defaults to 0, but now let's do that. So this is nifty, but let's say that you still want a bit of variation between the normals that you have, and I don't know, it's all going too uniformly in one direction. you still want everything to go in that direction, but you want to mix it up a bit. There is a way that I do it that is actually really simple. So here's our current normal position. And one thing that you can do is, it is called an attribute randomize. And so first I want just a random normal right now. I want it to be going in any random position. So first I need to name the attribute that I want to randomize, which is n for normal, and I'm going to feed it into here. And so we can see that it is giving me a random position. It's not quite the randomness that I want, and the way I usually do it is inside sphere. So that truly gives me a random value within 360 degrees. So now if we were to plug into this, we could see, yeah, everything is completely random. And we don't want that, but we can use this. So I'm going to plug this into the second input, or input 1. And so now I want to blend between what I have in the first input and the second input, or input 0 and 1. So we are going to do @n equals, and the function is a linear interpolation. So we're just going to go just from 0 to 1, just blending between one value and the other, and it is lerp, linear interpolation. And so first we need the first attribute that we're going to blend, which would be the normal that we have now. Then we want the normal of the second input, or input 1. So we'll do what we did before, where we go point, first input, or input 1, and then we want the normal of that input and correspond to ptnum. So now we have the two attributes that we want to blend between, and then we need a bias, or basically how does it know how to blend? We need a number from 0 to 1. So we're going to make a new float, and we're going to call it bias. So now we can vary it up as much or as little as we want. So now I can go whoop, and now everything's crazy, or I can mix it up. Another thing is, so the values here, they are not normalized. So you can see that they're much longer than 0 to 1. So one thing that we can do to just make it so everything is from 0 to 1 is we're going to normalize it. So this makes it a little bit easier to kind of understand what's going on. And now when we have these connected, now they're all random. And now if we merge, now you have all these random pillars just resting on your grid. And so the way that we did this is the way that I do a lot of things throughout the day. So next we're going to be putting this to use in a particle simulation.